Greetings, my friends.
Good morning.
Hey, good morning.
Morning, good morning. It is Monday morning and you do not have to wait any longer to do calculus.
What a blessing.
I know. Well, I was exceedingly impressed with your stellar tests as a whole. That was amazing. And on a side note, as a teacher, I'm actually glad to see that. I mean, some teachers' attitude about, I think the average on that test was, I don't know, like 92% or something like that. Some teachers would think, uh-oh, I didn't make the test hard enough. That's not how I think. I think, good job. Like you understood the important parts of this. As I mentioned, and I want to show you this just quickly because it's kind of cool. I could have made this hard. Let me see. Pulling up the key. The last question, the last question, the extra credit, which is gone. There it is. I just want to play with that just for a second before we launch into something else. Let's see if I shared a screen yet. No, working on it. Just because this is kind of neat to see. So people were pretty successful. Let me see, I'm not really exactly looking at the key here, but I think question 5 was asking you to find the expansion, the Taylor approximation for the function f of x equals x natural log of x. And again, I think this is the best takeaway for this is not so much can you steal the idea from somewhere else, but can you just make it for yourself? Can you do it from scratch? And you didn't have a choice but to do this one from scratch simply because natural log of x wasn't one of your expansions. If you had an expansion for that, well, maybe it would be because you could replace x with x minus 1, but anyway, won't go down that road. And long story short, you ended up with, if things went well, you ended up with x minus 1 plus 1/2 times x minus 1 squared. And so this is the power, and we're leaving this now. Goodbye, power rule, power series. And so this is just kind of a good one to sort of leave on because it kind of shows so many cool things. But one, it shows that, and if I say dot, 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 meaning it keeps on going, it shows in this case that, hey, look, the series is alternating. Well, kind of. Did you notice the first one's not? Like the first two are actually both plus signs, and then it goes kind of plus minus from there. So it's an alternating series. The other thing is the coefficients aren't very, I don't know, they're not automatic because your derivatives produced kind of such strange numbers. It is a wonderful extra credit question because it's doable to see if you could come up with the, well, not the sort of dot, 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 because would you agree dot, dot, dot is only semi-helpful in the sense that you might know, well, you sort of should know that the next term would be x minus 1 to the 6th. And because it's minus 1/20th, you should know that the next term is plus. But the coefficient is not obvious. Do you agree with that? Because it's not an arithmetic sequence. Let's see, plus 4. This is not plus 4. This is plus 6. And so it's not arithmetic. It's not geometric because if I said 2 times 3 is 6, 6 times 3 is not 12. It's 6 times 2. So it's not geometric or arithmetic. So it's very kind of hard to tell what's going on. So what's that next term? Well, see, that's the hard part. I mean, that's the challenge here. And I can't remember because I haven't thought about this for a couple of days, but it did occur to me based on what you noticed, and you would have had to have noticed this when you were building this sequence. But in the end, what you did when you took a derivative is the coefficient that was kind of, or the exponent that was up here, if you will, kind of ended up multiplied by that number. And so the end result is, one way or another, you'd actually have to notice that, hey, that 12 is 4 times 3, and that 6 is 3 times 2, and that 20 is 5 times 4. Notice there's kind of a pattern to that. So the next one apparently then would be 6 times 5, it must be 30, right? So this next one would be 1 over 30. You'd have to recognize that pattern, and that's very difficult to do, but it is doable in this problem. Many of these problems it's not. And so what might the actual, and again, I also want to leave you, because these are the things that I could have tested you on, as I said, and made this harder. And I actually do want you to kind of understand them. So I'm not just doing this to do it. I sort of want you to leave you with a little bit of deeper understanding of infinite series in case you go on in this. And so, well, I see the alternation, for instance. So, I'm kind of minded to sort of start normal. And so this is a thinking that you should have gone through. Let's see, I see alternation. So, maybe it's to the n power, to the n plus 1 power. But again, I'm a little bothered by the fact that these are both plus signs right here. So that feels kind of troubling. And then I see let's see, well, if this is 4 times 3, then isn't that number on the bottom, since this is a 4 and that was a 4, isn't that number on the bottom n times n minus 1? Isn't that what's happening? Like this is the 5th, and that's 5 times 5 minus 1. So that's kind of what's going on. Let's see, let's work this back then. So this one is 2 times 1. Yeah, that's working. But then this one would be 1 times 0. Notice that's not working. That's not good. So it's like I thought I had it, but then that first one doesn't follow the pattern. Do you agree with that? And so that's difficult. I don't know what to do with that first one. You should be thinking. And then of course, this part's pretty easy. In other words, it's just x minus 1 to the nth power. So it's like I'm kind of there. Let's see, if I start at 0, does this work? Well, I don't know, let's start at 2. If I put 2 here, I just want to see if it's working. If I stick a 2 here, so that'd be -1 squared, which would be positive. Okay, that's good. And I'd have 2 times 2 minus 1, which is 2, so that's good. And then I'd have x minus 1 squared. It's working at 2. So this is actually working at 2. Is it working at 3? -1 cubed would be a negative number. Good. Oh, down here I'd have 3 times 2. That'd be 6. That'd be good. Okay, that's working. And then x minus 1 to the third, it's working. So this is actually working well from there on, but it's kind of not working out front. Does that make sense? It's not really working there. So what does that mean? Well, that's actually a genuine change of pattern. I'm not going to go back through this, but what happened early on when you were making this formula, if you will, was the derivatives kind of fell into a pattern, but they didn't fall into the pattern immediately. And so you could actually solve this because this is broken, if you will, you could actually solve this by just saying, well, fine, let's start at 2 then. And we'll just go back and add this to it. Just add the x minus 1 to it. That actually works. Now, again, you should leave this also thinking, well, that's wonderful, but who cares? Like, why would you ever need that for anything? I mean, good for you. But 2 reasons. One of them is you saw in Desmos how if you do this, you can sort of get more terms, right? I mean, you can get all the terms you want, if you will, if you have some reason to be really accurate. But the more important reason that we touched on, but just didn't go super deeply into, is the radius of convergence. Now on the test, I actually asked you, excuse me, to find an estimate for f of 2. Now, again, in your world with calculators and so forth, you would say, I don't need an estimate for that. I'll just take 2 times the natural log of 2 on my calculator. It's really simple for us. But remember, thousands of years before this, nobody could ever do that. They didn't know what the natural log of 2 was. And so this is cool that you could actually plug this into Well, our blue statement back here, just plug 2 into that. And notice I picked 2 because that was really nice. Did you notice how easy that made it? Because 2 minus 1 is 1, and then 1 cubed, and 1 to the 4th, and 1 to the 5th. It's like, don't even have to do it. And so you really just end up with, 1 for this term plus 1/2 for the next term minus 1/6 plus 1/12 minus 1/20. And so that's fun. And so you just add that up, and you could actually, write that down as a decimal or a fraction. And now you actually have an estimate for 2 times the natural log of 2. And so that's kind of fun. That's kind of the takeaway from this historically. And let's see, who sent me that? Was it Adrian? I can't remember. Again, this is why your calculator has a logarithm button. Do you understand that? Like, your calculator would not be producing natural log of 2, because obviously that's the hard part, natural log of 2 without a series like this. And so that's amazing that it can do that. But again, the radius of convergence, I chose 2, and I actually didn't notice this until I made the key after you took the test, but it's a good thing I chose 2, because you can't plug anything you want into this. Let's take a quick look at it. In Desmos. So let's graph.
Oh, I thought the 2 thing was on purpose, just because of how neatly it turned out.
That's why I chose 2, because I just wanted to make it super simple for you. But I could have chosen 3, but had I chosen 3, it wouldn't have worked. And I didn't know that till I kind of played around with this a little bit, just trying to deepen my understanding. So let's see. So I'm going to say x plus 1, x plus 1, x plus 1. Can I say x plus 1? Yeah, I can say x plus 1 minus 1. So I'm just going to type out the sigma that we just did a minute ago, plus sigma. I hope I can do this in this world. I've done sigma in this world, haven't I? So we started at 2, and we say we can't go to infinity, so I'll just go to 4 for now. And then we have parenthesis -1 raised to the n power. Get out of there, divided by n times n minus 1. Let's see, n minus 1, close parenthesis, get out of there, go to x minus 1. We're getting close now. Raised to the nth power. Boom. So how do we know this is right? Well, we know it's right, or at least we're checking to see if it's right. This isn't letting me keep going here, because we're comparing it to the graph of y equals x natural log of x, since we live in the modern world. X natural log, where's natural log? Is it in here? Yes, it is. So remember this, that this thing was centered at 1. So we expect it to look just like it at 1. And so what happens? What happens if I start increasing? How do I get up there? This is not good. Arrows, I guess. Can't just move up there. If I take it to say 8. So that's 3 more terms than you just added, right? So notice it is looking like, and I'll see if I can stretch it out. There we go. Stretch it out a little bit so you can see that it's looking really good. It's looking like a really close match. Remember, the purple graph is the accurate graph. The green graph is an approximation. So can you see why 2 was a good answer then when I chose 2? But at this point, you don't want to choose 3. Does that make sense? Because the green graph, which is our model, is not a close match to the purple graph. Okay, well, let's just add more terms, you say. Let's go to 25 terms. Do you notice it doesn't seem to want to play nice?
Is that E it's getting stuck at?
Yeah, what's it getting stuck at? I like your thinking. Do you see how the green graph wanted to bail off of the purple graph? It wanted to bail off it. Like right now, it looks like about 2.4. And so, Vale's wondering, is it bailing off at E? Because E is 2.7. And so the answer to that could be yes. We're not really sure. Notice this makes a ridiculously good answer for 2, right? If I get really close to 2, notice how good that is. They both come up with really good approximations. Well, it turns out this is never going to match up. Like it's not going to match the purple graph. It only has a radius of convergence of 1, meaning we centered it at 1. You can only go 1 either way. So it has an interval of convergence of 0 to 2. In other words, I asked you to find f of 2. Whew, that was lucky, because if I'd have said 3, it wouldn't have been close at all. You can only plug in 0 to 2.
So you would have just had to use a different A in order to solve for 3, right? You would have used, well, 3.
Nice job. Exactly right. It's not like this had to be centered at 1. Does it make sense what Vale just said? All I have to do is just move it to some new location. If I want to know 3, then just move it over close to 3. Make it 3 for that matter. Great. Yeah, that's exactly right. So the reason I'm showing you this is because of this radius of convergence idea. In other words, how are you ever supposed to know that? Like, how would you know? We're playing around, but remember the ancients did not have Desmos to be able to sort of cheat and look at the graph and discover that, if you will. And I'd encourage you to play with Desmos and take that up to higher than 25. It never works. Like it does not match the other graph outside of 0 to 2. It'll match 0 to 2 better and better and better, but it's just terrible after that. Takes off to infinity. Well, I'm not going to do this for you just because I don't want to take the time today. But remember, I said you can get the radius of convergence by looking at the ratio test. Remember, the ratio test said that if you take a of n plus 1 and divide it by a of n, in other words, the next term divided by the previous term, and that approaches a limit which is less than 1. In other words, they're behaving similarly. If those behave similarly, if they approach something less than 1, then we said that converged to something. Well, I guess for us, and remember that's not part of the alternation is not part of the a of n. So if I just write out what the ratio test would say, then let's see, wouldn't that be x plus, minus, I'm just writing what's up there as a fraction, x minus 1 to the n plus 1 divided by not n, but n plus 1, and not n minus 1, but n minus 1, well, plus 1. So there's my a to the n plus 1. And then my a to the n would be x minus 1 to the n over n times n minus 1. So there's my statement. Maybe I will play with this a little bit. We'll see how far we go. So then if I divided those, I'd have the top over n plus 1, and then n minus 1 plus 1 would be that. And then I'd be multiplying by the reciprocal, correct? Forgot the plus 1 up here. Are you tracking with this? This is the thing that would have made everybody go from an A to a B had I, if you will, insisted on this last part. Okay, well, what happens to that? What happens to that statement right there as n goes to infinity? N goes to infinity. What happens to this thing? Well, notice there's some cool stuff that you can do to make sense of this. One of them is, hey, look, n divided by n. Infinity divided by infinity, that's going to cancel out. And then let's see, what about that x minus 1 to the n plus 1. Isn't that x minus 1 to the n times x minus 1 to the 1? Isn't that how exponents work? And then I still have an n minus 1 on top. And on the bottom, I have an n plus 1. And on the bottom, I have an x minus 1 to the n. Well, hey, that's good news because now I can actually get rid of those. As a side note, what happens to n minus 1 over n plus 1 as n goes to infinity? What happens to that?
It goes to 1.
Goes to 1. And by the way, that's why I canceled these. It's not that they cancel, it's that 1,000 over 1,000 is on its way to 1. So when you multiply by 1, it cancels, but it's on its way to 1. So this thing is on its way to 1, which means this whole thing then is on its way to x minus 1. You agree with that? In other words, this thing's going to behave like x minus 1. Well, remember what thing? It's not the equation, it's this. Well, remember, we need that to be less than 1, don't we? Well, when is that less than 1? Isn't that when this happens? And when I add 1, don't I get that? In other words, we need this thing to approach a limit less than 1. When's that going to happen? Well, the x didn't cancel out, so it only happens if x stays between 0 and 2. So technically, as a proof, or as, if you will, the deeper side of this, or what I didn't teach you, or at least didn't test you on, I showed you this a little bit. This is kind of a cool problem and shows you why the radius of convergence is so important. And so had I gotten unlucky, if you will, and asked you to find f of 3, that wouldn't have worked out so good, right? And hopefully I would have made the key first and then, saw that something was wrong and figured it out. But yes, going out the door, and in my opinion, this is the time to show this to you. Going out the door, can you see why this is an important concept? I don't think it's important if I show you on day 2, which is what I think is so wrong in books so much of the time. You've played with this stuff enough now and you get it well enough that you did pretty good on the test. And now if we look at sort of the little details, you can see that at times it's actually pretty darn important. And so that's not going to model the particular polynomial we had does not model x natural log of x unless you stay inside 0 to 2.
There is one thing that's bugging me. I'm confused on your sigma notation, why you went through, I guess, kind of a complex way, because when I did my sigma notation, I actually used the chart, took the natural log of x plus 1, and then kind of played with it to get
It's a wonderful idea.
that one.
I did the exact same thing.
And it does not look like what yours is.
Yeah, that's a wonderful approach. And it shows, if you will, like what I noticed as a part of taking derivatives, I just noticed this happening. But you guys are saying, and Raymond, we may need to talk after class because I didn't really have much of a sense of where yours came from.
Yeah, I've sent an email.
Oh, good.
about
Okay. Where am I trying to go here?
Because I was mostly just doing all my work on Desmos. So I was just moving the numbers
You need
around.
the common power series expansions sheet, I think.
I must have gotten rid of that for some reason since I thought we were done with it, which we sort of are. So yeah, that's a good idea too. And actually I didn't investigate that, but just so that you're, thinking, do you understand what these two folks are saying? They're saying that, well, we don't have the natural log of x, but we do have either the natural log of x plus 1. And so, we have minus 1. So is there some way I could kind of modify that series since, we sort of have the answer for it already, like in the sense someone else did it for us? or perhaps this one looks really close, except for it's, you know, a negative, like the X needs to, the sign needs to be changed. And so both Eve and Raymond are saying they played around with this and had some success with that too, since, you know, these are given. So that's awesome. Yeah, didn't think of that. It's not the way I approached it. I just sort of played around with it till I got it to work. And I did have to play around with it. I didn't just immediately write it down. Took me a while to say, well, I wonder if I could just ignore that first term and write it out there. If there's some way you don't have to ignore it, because I did. I just left the dang thing out and said, well, let's just stick it on at the end. And as a side note, didn't I just ignore that down here? Didn't I just do all this and like pretend it wasn't out there? Is that fair? Didn't I kind of just forget about that? You with me there? Oops, forgot about this.
Shouldn't matter.
Is that okay or not okay? Is that an accident? Or did I do that on purpose?
Feels like it should be not okay.
Does feel like it should be not okay. However, remember convergence, we don't care what's out here because we're just wanting to know, does this add up to something? And so if X was 10,000 or 100,000, well, fine, you add 100,000 to it. That's still not a very big number in light of infinity. Does that make sense? Like it doesn't matter what you put in for X. X is like X is your 2. Remember I said find f of 2. X is some number that you're going to stick in to use as a model. So I did not ignore that on accident. It doesn't make any difference as far as convergence is concerned. Now it makes a huge difference to Eve's point about your final answer. Does that make sense? Like in my case, if I put 2 in, don't I have to put 2 in out here, and 2 minus 1 is 1. So that means I better add 1 to my final answer. It matters in your final answer, but it doesn't matter as to whether it actually converges to something. Does that make sense? So there is, you know, more that could be said in this section, but I think, and I think in terms of how math should be taught for you future math teachers, don't show people all the weird details. Don't tell them that the square root of x squared is not actually equal to x, it's equal to the absolute value of x. Don't tell them that at the start. Like play around with it and help them understand how easy a square root is. Let them think the square root of x squared is just x for a long time. And then later, you know, oh yeah, there's this one little caveat or this one little detail. Show them the detail stuff later when they actually understand it. Otherwise, this stuff just looks totally confusing. A good example of that with respect to Calc 1, for those of you I had, just as an example, there's an entire chapter on the concept of a limit. And it's very theoretical. And I even completely skipped one of the sections in there that just destroys people. Like they're done with calculus before they even start. I mean, mentally. And you know, in terms of their emotional engagement with the material and how beautiful it is to, you know, find a derivative. Find a derivative is just a cool way to find the slope of a line. But they get, you know, you get lost with these details about what a limit is theoretically before you even get a chance to see the beauty. Anyway. So today, my friends, we say goodbye to the infinite series, which is sad. We're sad to see it go. But now we must press on to something extremely cool in chapter 12. And the first part of chapter 12 is a parametric, something called a parametric equation. And advanced math and physics makes a ton of use of this. And I'm going to show you how today. If you've had physics, part of what I'm going to show you today won't be anything new. And then we're also going to look at something called a polar equation in the sections that come up. And so a parametric equation is actually pretty simple in concept. And here's the idea. Let's make an equation where the x term and the y term are not found relative to each other. Now think about this. What you're used to seeing is an equation where y is equal to 3x plus 2, which sort of means you can pick x to be anything you want. If you will, x is, mathematicians would call that the independent variable. Independent And so you pick X to be anything you want, but in order to get Y, you have to know X. Does that make sense? A parametric equation, though, is where you say X is found separately from Y. You find them totally separately. There's this extra, well, parameter. That's where the word parametric comes from, parameter. And that parameter is often time. And that's why this is so cool and so practical. So we might say something like, well, let's let X be, I don't know, how about 4t squared? And let's let Y be 3t minus 2. So I'm making that up. So they're found entirely independently of each other. Now, if t is time, then let's play around with this a little bit. This is so easy. This is not complicated. You don't really need, right now, this doesn't even look like calculus. Like, why do we need to be, what was this doing in a calculus class? You could teach this to anybody that knows basic algebra. So let's just make a little chart. Let's make a little table of what these things look like. So there's t, and then I guess we have to have a place for X and for Y. And so since t is time, let's let time march along in the positive direction. So, maybe these are seconds or something like that. And so 0, well, notice the X coordinate is 0, but the Y coordinate is -2. So your first point, your first ordered pair is 0, -2. And so if I just draw kind of a lame graph of this really quickly, then there's our first point. And then you go to 1 second, now X comes to life and becomes 4, and Y goes to 1. And so I'm at the point 4, 1. So I guess I'm out here, maybe you're right about there. So I went from one point to the next. So my question to you is, how did I get there? Because there's other times between 0 and 1, right? Like there's 0.5 seconds. Do you think that I got there by going in a straight line, like there's the rest of the points? Or do you think that I got there by like curving upwards to it? Or perhaps curving downwards? Like we don't know that right now, but there's many points in between here, right? We could, that was a mistake. We could go back and stick 0.5 in there to answer the question that I just posed, if you will.
Couldn't we do algebra 2 stuff and make it solve for t in one of the equations and then substitute out and
That's
just have
exactly.
one equation?
Yep. And so the cool thing about parametric equations is that actually you can go back and forth. You can convert from parametric to rectangular. Rectangular is what you're used to with just X's and Y's, and we are going to do that. So let's see, when X is 2, notice, or when Y is 2, I'm sorry, T is 2, notice X goes up to 16, and all of a sudden I'm realizing, whoa, my graph is going to get huge. And when X is 2, 6 minus 2 is 4, so 16, 4 is kind of my next point, kind of way out there. And so that's what's going on. So that's kind of what this thing is starting to look like. Let's go back, since my numbers are so huge anyway. Let's go back and see, what if I did 0.5? 4.5 squared is actually a fourth. This is 1, and 3 times half is 1.5. So that's -1. Is that right? -1.5. Why am I struggling? -1.5 minus 0.5. So I'm at 1, but then minus 0.5. And so actually this is not straight. This is actually kind of curved. It appears it's kind of curved. Why is it not surprising it's curved? Even as a rough graph?
Because of the squared.
Because of the squared, right? And we sort of know what squared looks like a little bit. And so maybe there's some intuition. But let's go see what Desmos has to say about this. I need to show you this in your graphing calculator as well as Desmos, but in Desmos, this is the way you graph parametric equations. You just write the equation out like it says. In other words, you list the XY coordinates. So our X coordinate was 4 times T squared. And so T is your parameter, T squared, comma, there's my X coordinate. My Y coordinate was 3T minus 2. Sheesh. Come on, man. So there's the graph we were making. I notice it finds all the other points. Like we just found a few, but it finds t is 0.1 and 0.2 and 0.3 and kind of connects them all and so forth. So that's interesting. Let's do this right now. So to Vale's point, could we convert this? This is part of your homework assignment. Could we convert this to rectangular? Rectangular meaning, you know, X's and Y's. Could do that? Yeah. All you have to do is solve one of them for t and then plug it into the other one. So since y is equal to 3t minus 2, it's only t, not t squared. It seems easier. I don't know. I guess that's debatable. Seems easier to solve the bottom. Well, maybe I'll solve the top one. So x equals 4t squared. So I'd have to divide by 4 and I'd have t squared. And then if I took the square root, I'd have the square root of x over 2. I can't take the square root of x, but I can take the square root of 4. So that's kind of lucky. So there's what t is. So then if I plug that down into the y equals 3t minus 2 equation, plug that into 4t, then don't I get the square root? I get 3 over 2 times the square root of x minus 2. Same graph. Y equals 3 divided by 2. Get out of there. Square root of x. The 2 was not inside the square root. Look at that. They're the same exact graph. It's right on top of that other graph. Now, are they really the same though? And this is why parametric equations are so powerful. Notice there's no more time. Like the graph just is the graph. There it is. It just takes off and, you know, kind of goes forever. Are they really the same graph? And I would argue, no, they're not. Here's why. Watch this fun business. If I go up here and throw in a parent, I say I want to let this thing go from not time 0 to 1, which was there by default. I didn't even look at that. It was like 0 to 1 second. What if I say, let's go from 0 to c? And maybe I'll further limit c to go from 0 up to 5 seconds, if we're going to call these seconds. So now it starts at 0. So notice the graph doesn't exist yet, if you will. And I'm going to stretch this out a little bit so it shows a little bit nicer. They're not really the same. What I would like you to do is kind of watch. I forgot it started at -2. Watch it kind of grow. In other words, do you see that parametric equations have some motion to them? In other words, this is actually modeling something flying through the air. Imagine just say a housefly buzzing around in your house. It's not, the fly is not everywhere in the house at once. I mean, it's not a graph that lives in your house. It's cruising along, and at any point in time, it's in a certain point in space. And so leaving t in it, leaving that parameter of time in it, is a really powerful concept because it has directionality. So this graph before didn't have any direction to it, but does it make sense? This actually has arrows on it. It's got a direction. It started at 0, -2, and it's flying, if you will, along the curve in that direction. And so I can choose how long I want the time to go. So if I take it out to say, I don't know, 1.9, since I stopped right there, notice the graph doesn't just keep going. And so, but the red graph does, it goes forever because it's assumed x is everything, right? X can't be negative because you can't take the square root of a negative, but it's everywhere it can possibly be. So the graph goes forever, whereas the black graph does not go forever. It stops when you stop the time. So there is a difference, and it's kind of a powerful concept, but it's not hard. This is easy. Let's throw that in the notes really quick. Any thoughts that you have on that subject that you would like to weigh in on? Are you feeling it?
Looking good.
This makes me think of, do you remember in Calc 1 when we had to do the linear line that goes along that one graph? Do you remember that? That was a long time ago. This kind of makes me think of polar graphs and like how they move, you know?
Exactly right. Yeah, we studied polar and we're going to look at derivatives and so forth of that here coming up. And so, yeah, this is kind of cool. So there's directionality to this. You should be able to add arrows to these graphs, and that's a part of the concept here. So parametric. Graphs have direction. Directionality, is that a word? Seems like it should be. So that's kind of cool. So you can convert back and forth. That's just kind of interesting. The other side of this, to Eve's point, is you can come up with some really crazy kind of fun graphs when you start throwing other things in. And so let's go do that really quick. Let's leave C in there. What do you think this graph's going to look like if let's say, and again, I would encourage you just to kind of play with this on your own time, like, and just screw around, because that's kind of the fun of all of this. But if I just start making stuff up, I don't know. Let's go. Let's try like the sine of t. So my x coordinate will just be the sine of t, comma, and my y coordinate, I don't know, let's make it kind of simple, like t squared plus 2 or something like that. What happens if the x coordinate is based kind of on a sine wave, but then the y coordinate is based on like a parabola or something like that? So I'll make it like t squared plus 2 or something like that. Let's see what that does. Let's make it plus 1. So what's going on with this? Well, one of the things I think I need to do is go into radians just so that it behaves a little more nicely. But so notice it appears to start at 0, 1. Can you quickly go, well, of course it starts at 0, 1. At time 0, sine of 0 is 0. T squared plus 1 at t is 0 is 1. 0, 1. That's the first point. Of course it starts at 0, 1. This is not rocket science. And then you could go to, t is 0.36 and so forth. And so this thing begins to, again, I like to think of this something flying just because it's, taken off. But the question is, where's it going to go from here? Right now, you should think, well, it's a parabola. But what's the, how does sine get involved? Or does it get involved? Well, apparently it's getting involved because can you see it's not a parabola anymore? Because it's actually curving inwards now. And just because I'll just stretch it out so we can sort of see that. Clearly it's not a parabola. So you should be thinking, I wonder what effect sine is actually having. So this is kind of fun. What kind of a graph is this that it's being made here? So it looks like it's kind of almost behaving like a weird sine wave along the y-axis, if you will. That's kind of fun, right? Does it just keep going up? What does it do? Does it turn around and come back down? I mean, what happens to it? So you really do get some kind of crazy graphs. I could go in here just quickly to answer that question. So you take it out to 15 so that I can go further. Notice it appears to just be kind of going up and taking off. So that's kind of fun. Do you understand with respect to calculus though, like why this just creates fun graphs? I mean, if you're just playing with it, it just creates fun graphs. But we might have all the same questions we had before, like what's the arc length of that graph, say from back up to say 6. Does it make sense? It might be an interesting question to ask what the arc length of that is right there. Because again, if this is something flying along that path, it'd be kind of cool if we could know how long it was, like how long was the flight? Or we might say, I'm interested in slope. Like, you know, one of the places that's kind of interesting is kind of right here. Like, you know, isn't the slope vertical right there? Like where is the slope actually vertical? Or, you know, just what's the slope at 1 second, something like that. So I might want to know what the slope is. I might want to know what the arc length is. That's why this is in calculus. So you may have seen this a little bit before in Math 112 if your teacher made sure you had time to cover this, which I hope they did. I always feel like they should. Maybe that part, maybe what I just showed you isn't new, but can you see where calculus comes in? Because we just have the ability to answer more interesting questions about this that other people can't maybe answer. So if this was a fly flying across the room, it'd be like, well, when was it flying vertically or something like that, or a jet or whatever? Or when was it flying horizontally? Those kinds of questions. That's kind of what we're going to tackle. Well, let's tackle some of that right now. There's nothing wrong with this graph. I like it. Let's just stick with it for a second. And I want you, while I'm sort of copying this into the notes, to think, how would we figure out the slope? Like, how are we going to take a derivative in this world? How might that work?
The answer is we don't, and move on.
Yes, that is awesome. I love that. Good news, friends. It's impossible. That's hilarious. So I will write out just so that this is how. That's really the way it's written. So based on the parameter t, so we established this has directionality and so forth. And so what about a derivative? What about slope? Remember, that's what that's code for. We tell everyone else outside of this class that we're taking a derivative because it makes it sound really complicated, but all we're really doing is finding slope. Well, would you agree? This is actually pretty easy. Would you agree that the slope was always dy over dx? It was how much did y change over how much does x change? And remember, the d is sort of code for tiny change. It's not just any old change, it's a tiny change. And so would you agree you don't need calculus to do this, in the sense that if you said you were interested in, I'm going to zoom in on this, if you said you're interested in it, say, notice I can't really tell what time it is here. I was about to say at time 1 second, but I don't know where I am at 1 second. But does it make sense if you went from 1 second to 1.1 seconds? That'd be 2 ordered pairs that are really close to each other. And then you could just find the slope of those 2 ordered pairs and you'd have a reasonable estimate for that. Does that concept make sense? That's all slope is. Don't forget that. And if you wanted to be really accurate, then go from, and let's do this just for the fun of it, even though it won't be fun. Let's say we want to find the slope at t equals 1 second. Again, it's fun that we don't really know where that is on this graph, right? Unless we go back and think about it a little bit. So let's just find at t equals 1, what point am I at? Well, if I bust out my calculator, which is apparently lost somewhere, since our equation was the sine of 1 and then 1 squared plus 1, so my calculator is in radian mode as of right now. If I take the sine of 1, I get 0.841. And if I put 1 into t squared plus 1, I get 2. So I'm at that point. And then let's get a pretty good answer. Let's go to 1.01. In other words, let's not let much time pass. Let's let 1/100th of a second pass. So what's the sine of 1.01? Well, I get almost the same answer, of course. I get 0.8468. I'm going to call it 0.847. I'm also wondering, since I was such a small amount of time, if I should be rounding these further out. And then 1.01 squared plus 1 is still about 2, but it's 2.0201. And so you know how to find the slope. Y minus y over x minus x. I'm just going to do it. So I get 0.0201 over 0.006. 0201, 0.006. I got 3.35. So would you agree that's an estimate for my slope at t equals 1 second? So I'm wondering, you know, where was I at 1 second? Let's go back and look at that on Desmos to see if that even looks reasonable. I'm going to go to 1 second now. Remember I distorted my graph, so I'm going to go fix that. Go into Zoom Square. So we stopped right at the top of that graph. Does that make sense? Does that look like the slope is 3.35? Well, it's positive and it's, you know, biggish. It's more than 1, right? So yeah, that looks reasonable. Say that looks reasonable. So that's kind of cool. So again, realistically, you don't need calculus to do calculus. Do you still understand how simple this really is, or did you get lost in calculus taking derivatives and sort of forget what you were even doing? But watch how easy this is. It's really cool. How do you do it mo better? Well, if dy dx is what we're after, then isn't that the same as dy dt divided by dx dt? Since dy dt divided by a fraction is the same as them being multiplied by the reciprocal. In other words, we can't find dy dx because we don't have an equation with y's and x's. We have equations with y's and t's and x's and t's. And so this seems to be telling us that if I take the derivative of y with respect to t and divide it by the derivative of x with respect to t and divide them, that I'd be able to find the slope kind of in a much better way. Like I could get a much better answer. I don't have to do all this embarrassing guessing and checking. So since our equation was dy or y equals t squared plus 1, isn't dy dt equal to 2t plus nothing? And since x was sine, the derivative of sine is cosine. So we're saying, okay, then dy dx is found by dividing those two. There's our, what did I get a 3? There's our equation, our derivative. Remember, we call it a derivative, but it just means a slope finder. So easy. We got an equation to find the slope. Go ahead.
Sorry. Would we get the same equation? I know technically they're not the same graphs, but if we kind of did what we did before and manipulate it with algebra and then take the derivative, would we get the same thing?
Wonderful question. Everybody understand Eve's question? Could I get rid of the t by solving one of them for t, plug it in? So now I have an equation with what y is and x is, and then I could just find dy dx in the normal way. Yep, you'll get the same exact answer. The only difficulty is like, where am I? Does that make sense? In other words, you'd have to, because you can't use t equals 1 anymore. So you'd have to think, well, great, now I found this equation, but what ordered pair am I at? Do you see what I'm saying? You'd have to plug 1 in to this statement right here to get the answer, to get the x and y point that you're at, so that then you'd know what point you're at for the slope. Does that make sense? It's not going to be 1. You don't get to plug 1 in because that's a time, not an x or not a y. So great. Well, now we can find it. So our slope at t equals 1 is apparently equal to, not approximately, 2 times 1 over the cosine of 1. What does your calculator say that is? I bet it's around 3. 2 divided by the cosine of 1. My calculator says that's 3.7016. Now, it might bother you a little bit that it's like, wait a second, you're just writing it as an approximation again. But we're not. It's 2 over the cosine of 1. I mean, that's the exact slope. It just happens that in this case, cosine is like logarithm. We don't, in a sense, we don't know what it is. Perhaps you're a little more impressed now with the calculator spitting out the cosine of 1, and you realize, of course, it's a decimal because it's an infinite series. And so, do you notice that our answer, wasn't so hot? Probably because 0.06 is such a tiny number. I should have rounded those better. Does that make sense? If I wrote 0.841 and 0.847 out to maybe 5 or 6 decimal places, I bet I would have got an answer closer to 8.7 because I'm sorry, to 3.7, because this is a really small change of time. Isn't it 1/100th of a second? That's a tiny change. I should have got a better answer to that. So you go do that really quick and see if you don't get a better answer. But it's kind of cool that we, don't have to guess. So that's actually not real tough, right? Like, oh yeah, I can do that. I can find the slope of the curve any place that I want to go. That's kind of awesome. That's easy. Well, let's go take a look at an application for this that's really powerful. If you haven't seen this from physics, where people actually do this. So I'm teaching dynamics engineering right now, and we're using this, well, right now because it models what mathematicians call projectile motion. So let's make up an example about that right now. Application projectile. This is probably the most classic application of this. Projectile motion. I don't know if you know this, but when things fly through the air, what happens in the horizontal direction and what happens vertically are independent of each other. So let's make up something even more real than your assignment, just because it's kind of cool. I've mentioned that I like to ride mountain bikes, and I was just up on Mount Ashland last weekend with some guys, and there was a kid up there who was like 20, and he went over this huge jump. I do not have the courage to go over this, but the whole thing about it was, landing in the right spot where you don't crash. But anyway, that's another story. Let's say this jump, you don't have to know this much in your math assignment. I'll show you where your math assignment kicks in. But let's say the jump kicks you up in the air at, say, a 32-degree angle. And let's say at the time you're traveling 18 feet per second. I kind of wanted to put it in miles per hour, but I'll just leave it at 18 feet per second. And so that's all you would really know. Does it make sense that if you had a speedometer on your bike and you just went out there with a protractor, you could measure those things? Okay, so what's going to happen? Like, where am I going to land? That's my question, because realistically, this is what mountain bike jumps look like. You take off right there, but then there's like a big gap and a double. And what you don't want to do is land right here, because you're going to come to a complete stop. Your teeth are going to go into the handlebars. You're going to fly. What you want to do is hit it hard enough that you land over here somewhere where your reconnection to the ground doesn't cause you to stop so quickly. So most of jumping on a skis or a mountain bike or of that nature has to do with how fast do I go, since I can't really control the angle of the jump. How fast do I go to land where I want to land so that life doesn't suck? So you just foolishly decide you're going to go 18 feet per second, hope for the best. Well, here's what's cool. So it turns out that your x coordinate equals your speed. Actually, let me fix this. So what you have to do is break your speed into its horizontal and vertical components. Again, you don't have to do this in your assignment, but we're doing it in my physics class right now. And you might understand that that makes a right triangle right there. And this is what's so powerful about this. And the horizontal component down here of that would be the cosine of 32. So if you take 18 times the cosine of 32, I got to get my calculator into degree mode for this application. 18 cosine of 32, I get 15 point, I'm gonna round it off, 15.3. So what that means is most of your 18 feet per second speed, most of it's actually horizontal. What about vertical? Well, perhaps you see that that would be a sine problem. And so if I take 18 times the sine of 32, 18 sine of 32, I get 9.538. Again, I'll just roughly call it 9.5, just so we can have nice small numbers. And so if you actually want to figure out what's going to happen to you, you have to convert these into X and Y. You have to. X, Y components. And the reason for that is because nothing changes your horizontal speed. When you're flying through the air, your horizontal speed doesn't change. Your vertical speed, however, does change because of gravity. The Earth is trying to pull you back to the Earth. So there's actually two separate equations. One of them says 15.3 times time, because that's your speed. 15.3 feet per second times how many seconds you have will tell you how many feet you travel. So rate times time. So 15.3 is the rate, t is the time. So basically this is going to tell us our kind of our X distance for any time t. What's our Y distance? Well, it's also 9.5 times t. However, scoot that over. However, there is something changing here, and that's gravity. It turns out that gravity is pulling you down about 16.1. Gravity on Earth pulls 32.2 feet per second, and this equation has a 1/2 in it. So anyway, I won't belabor that point right now, but your equation for your Y distance as a function of time, X. Probably better to say this in the language you speak so that you're learning to speak it, but X as a function of t and Y as a function of t, because they're functions of that parameter. So you actually can't figure out how a tennis serve is hit, because the tennis serve is a ball flying through the air too. You give it an initial speed and initial direction, just like this mountain biker had an initial speed and initial direction. And then you just wait to see from there. So the negative 16.1 t squared is pulling back to the ground. Now you get to start right there. Like, as far as this isn't a physics class, you get to start with those two equations. And then what we're going to do is say, well, great, let's go see how that thing flies through the air. Now, here's the fun part. Let's see, I'll just totally make this up. Let's say this distance right here is 20 feet to sort of the place you'd like to land. And you just said, I'm just going to go in there at 18 feet per second and hope for the best. And then we'll say the trail just kind of flattens out from there. And so you're hoping you're going to land 20 feet horizontally 20 feet from there. Well, let's go look at the graph of this. Let's go look at the, and I almost don't want to do this, but I think I'm going to go over to your graphing calculator this time, just because I do want you to know how to do it in your graphing calculator, even though it's way worse of a piece of technology for this. But it's just kind of cool to know how to do it. So you got to go into, boy, I should have planned ahead. I don't know if I remember. Function, where is it? Is it format? No.
You're trying to find the Y equals button on the top left.
Yeah, it's a setting. I got to change a setting in this. I forgot which one it is though. Mode, dummy. You're in function mode. You've never noticed you're in function mode, but you're in function mode. Well, now you're going to be in parametric mode. And then tomorrow we're going to be in polar mode. So go to parametric mode. And what you'll notice when you go to the Y equals screen is now there's not just a Y1 and a Y2 and a Y3. There's an X1, as a function of time and a y1 as a function of time. And so we said our equation was 15.3 times, notice this button here, have you ever looked at that before? It says x, t, theta, n. You've always just hit that for your x, but now when you hit it, you're going to get a t because we're in parametric mode. And our y equation was 9.5 times t minus 16.1 times t squared. Bam, time to fly through the air. I'm going to graph and just see what happens. So great. So I'm flying, like, what does that mean? Well, let's fly through the air a little bit. Notice if you hit window, you have a choice. You notice this says you're going to fly from 0 to 6.28 seconds. I don't know how long to fly, so I'm gonna go down and just say I don't think I'm gonna be in the air more than 2 seconds. I've jumped my mountain bike a lot. And notice your time step. Do you want it to graph a point every 1 second, or do you want to go every 0.13 seconds? Again, I don't know where it got these numbers. They seem really random. I'm going to say 0.1 seconds. And I can even control the graph. Make the graph maybe a better size. But I'm just going to hit graph again and see where that leads me. So let's trace. Let's cruise along this thing a little bit. Notice it's kind of fun when you trace in this because it actually tells you the time of 0.1 seconds and it tells you where you are. So in 0.1 seconds later, I've flown 1.5 feet, and now I'm closer to the ground. Or I'm sorry, I'm up in the air a little bit. So I'm flying up in the air. Whoops, that wasn't right. And I flew a little further, flew a little higher in the air. Notice I reached a maximum height. Does it make sense? You might want to know where that is. That would be when dy dx equals 0. Wouldn't we be able to do calculus to find that point if we wanted to? And then you start to fly down and land back on the ground. And notice, roughly speaking, I was only in the air for 0.6 seconds. I flew 9 feet. And then I'm back on the ground. Well, notice I'm actually a little underground. And so did I make my 20-foot jump? Nope, I was going way too slow, apparently.
And you were only 1.4 feet in the air.
Yeah, above the jump. And that's because you took off so level. Does that make sense? It wasn't a very kind of a steep kicking kind of a jump. The other thing that, let me see, let me stop sharing that screen. The other thing that I, just out of simplicity, that I didn't include in this, and maybe I should have, is, does it make sense that we, by the equation that I wrote, I was kind of making that the XY axis right there. And so I was sort of trying to figure out when we got back to the ground again, and I was kind of hoping, and frankly, I thought I was going to overshoot this jump. I really did. I thought I was going to fly way, like way out there and land clear out on the right somewhere. Did I type it all in right? I can't remember. But that's really cool. It's powerful. So, does it make sense? You could actually go out and take a few measurements in the real world on a jump like that and actually know what speed you would need to go. What's interesting about mountain biking is mountain bikers do what they call towing each other in. So that's where you say, I'd like to jump that. I think I can do it, but I don't really know how fast to go. And I don't know math and calculus. And so how about you've jumped it? And so I'll just go behind you, and however fast you go, that's how fast I'll go. Like that's how mountain bikers do it. Because the consequences are so high of screwing it up. And you actually don't want to go too far either, because if you land out here in the flat, then you also get broken. You really don't want to land here. That's the worst place to land. But you secondly don't want to land out here either, because you'll usually bounce and flip over and go into the trees and stuff. Plus you're going way faster. You're sort of going too fast. But you see how powerful this is? So you have to separate these because gravity only pulls in the vertical direction. Are you aware of that? If you take a gun and you shoot a bullet and you drop a bullet at the same time you pull the trigger, the two bullets hit the ground at the same time. The one out of the gun is like, you know, half a mile away or whatever, but they hit the ground at the same time. Gravity pulls down on something independent of what it's doing horizontally. And it's only wind resistance that slows down your horizontal speed. And so you have to, if you want to model things flying through the air, you actually have to introduce the parameter of time, or you can't do it. That's what's so kind of cool about these problems. So since we have this up, and I don't think 18 feet per second is very fast. I found myself thinking 18 feet per second. Well, I think I put 18 because I was thinking of miles per hour. But if we converted that, that's probably really slow. I mean, that's probably the problem. I don't think in feet per second. But let's find the time to the top. In other words, right there. Well, isn't right there a slope equal to 0? And so can't I find dy dx and set it equal to 0 here? Now, we saw a second ago that I was only in the air for like 0.6 seconds or something like that. So it's a really short period of time. So, okay, well, let's find that. Isn't dx dt equal to 15.3? And dy dt is a little more complicated. It's 9.5 minus 32.2 t. And by the way, I showed you this in previous classes. I can't remember where or how, but these are actually velocities now. The change of x over time is a velocity. 15.3 is our velocity, right? Isn't that your horizontal velocity? And your vertical velocity, dy dt, is 9.5 minus gravity times t. Like, these are classic physics equations. And it's calculus that gives us those. And so now I can say I can put these two together to get dy dx. Notice you got to put the correct one on top. 9.5 minus 32.2 t over 15.3. So that's our slope. And I'm curious to see, when is that equal to 0, right? Because I want to know when the slope is equal to 0. And so, of course, that would happen when 9.5 minus 32, I'll get the 2 back in there, 32.2 t is equal to 0. Since it's only the numerator of the fraction. And so if I add 32, divide 9.5 by 32.2, I do get a number around half of 0.6 seconds, which is 0.295. So t equals 0.295 seconds. And so I know that's calculus in action. You can appreciate that's an important part of this. Another part that makes, you know, people that kind of do this stuff for a living really fun is, you know, to try to jump over something. Don't just jump over something. And so knowing how high you're actually going to get and where that would be, you could actually go out there and put some object like a tree or something in front of it and you jump over it. That makes it look really cool, right? So if you know some math, you could kind of predict, yeah, I'll land in this spot and I'll be this high in the air in the middle, and I know exactly where that's at. And so, yeah, I'll clear that tree and I'll still be able to land where I'm going to land. And then it makes your trick look awesome. Again, I'm just sort of, you know, showing you playful sports examples, but I can appreciate maybe it has a lot of other applications. Let's play around and do kind of one more maybe quick application with a graph that's, I don't know, let's just play around and see if we can come up with a fun graph. So let's see, I'm going to go in there and square that, and let's get cosine over here. what if we said like t, let's even give it a number. Let's make it like 2t plus the cosine of t. Wonder what that would look like. Is it going to be any fun? Cosine of t, boom, boom. Oops, too many booms. Make sure we can see it all. So again, it's kind of fun to go back to 0 and watch it jumping. And so it starts out at, and let's even go back and throw like a 3 in front of this just so it makes it a little more interesting. So if I throw a 3 in front of that at time 0, apparently I get the 0.31. So you're starting at 3,1. It's kind of like something jumped up in the air and started flying or something like that. Well, let's just see how this thing's going to behave as it flies. So that's kind of fun. It's kind of a crazy graph. Notice it kind of settled into, I don't know, kind of a sine wave, if you will, or like a vertical version of a sine wave. And so that's kind of fun, like that. Wonder what happened if I squared this t over here as well. Whoa, that's kind of fun. That's even more fun. I like that one better. Let's do that one. So this thing flies up in the air. Notice it does kind of a curly Q, and then it just makes, wow, that's awesome. It's almost like it starts turning into kind of circles. So that's kind of fun. Notice it has a whole bunch of places that have vertical slopes. And apparently those are when x is 2 and x is 4. But what times are those at vertical slopes? I'm going to give you a second to think about that. When are those vertical slopes? I'm going to go put this in the notes while you think about it. We'll answer that question and then we'll be done for today. Which is terrible because this is so cool. If you're not playing in math and asking and answering interesting questions, you're not doing math. And I did not make that example up ahead of time. I just wasn't faking it. I'm just playing around. This is really a cool graph. So I'm going to write those out so I can see them a little better. So our x coordinate is 3 plus the sine of t squared. Our y coordinate is 2t plus the cosine of t squared as well. So that's a really fun graph. Where is the slope vertical? Well, horizontal, it was when the slope was equal to 0, but vertical is a little rougher. Like I don't think you've ever answered this question. And the reason you haven't is because you can't have vertical graphs in rectangular coordinates. Like you never have that happen because it's not a function anymore. So this looks like a car spinning out of control on ice. Well, let's just go find the slope. I mean, we know what the slope is, right? So let's go find that. D, let's do it in the right order this time. The derivative of y, the derivative of 2t is 2. The derivative of cosine of junk is negative sine of the junk, but then times the derivative of the junk, right? Chain rule. So that's not a super simple derivative. So that's a complicated derivative. And then dx dt, the derivative of 3 is nothing. The derivative of sine of junk is cosine of junk. Again, times the derivative of the junk. So the derivative of t squared is 2t. So there's my two equations. And we said that dy dx was found by just taking the y slope, the y of t slope, dividing by the x of t slope. Sine of t squared over 2t cosine of t squared And we're wanting to know, when is that vertical? Anybody have any good ideas on that? I gave you a little time to think about that. What does vertical slope mean? This is rough.
Change in X over change in Y.
Yeah, maybe it's backwards. Isn't that a good thought that Vale just had? In other words, we said dy dx was equal to 0. He was wondering, and actually I don't know the answer to his question. He was wondering, well, what if we flipped them upside down and put y over the x over the top of y and set that equal to 0? I wonder if that would work. It's a brilliant idea, Vale. What is the slope of something vertical?
I think it would be infinity, wouldn't it?
Yeah,
Or-
isn't it infinity? When is this equal to infinity? What makes a fraction equal to infinity? This is why I've never liked the concept of people saying a fraction is undefined. This is really simple. If I told you you have a slope equal to 5 over 0, that's not undefined, just graph it. What happens if you start from a point and you rise 5 and you run 0? Doesn't that create a vertical slope? It's not undefined, it's infinite. We need the bottom to be 0, which, as it turns out, is exactly what Vale said. If you flip that fraction upside down and set the top equal to 0, Vale's idea would have worked. In the end, that's the answer to this question. When is the bottom equal to 0? And so when we wanted to know when the slope was equal to 0, we set the top equal to 0 because we don't care what's on the bottom, right? So if you have a fraction that's 5 over 0, we call that infinity. If you have a fraction that's 0 over 5, we say that's 0. So this would be a vertical slope. This would be a horizontal slope. And again, those are just interesting questions, right? Those are particularly interesting slopes. We could ask when the slope was equal to 1 and all kinds of other things, or we could say, what's the slope when t equals 0.2? And all those kind of questions are great. But particularly horizontal and vertical are really interesting. And so as it turns out, really, we just need to know, well, when the denominator is equal to 0. Brilliant idea, Vale. I'm impressed that you thought of that. It never occurred to me before. Oh, okay. Well, that's easy. 2t times the cosine of t squared has to be equal to 0. Would you agree that happens at t equals 0 for sure? Because of that t. So at time 0, was our slope vertical? Yep. Right when we started, our slope was vertical there, wasn't it? Now, a second later, it wasn't. It started to level out. But isn't it also vertical, you know, here and here and here and here, like a billion other places? Like, where's all those coming from? Where's all the other answers coming from? How's your math 112 skills?
Isn't the cosine of I don't remember. Is that cosine of 1 that's 0? Or is it?
Yeah, so there's a bunch of places where cosine is 0, right? And Eve is thinking, yeah, what about that other term right there? Well, let's remind ourselves. Cosine is which coordinate? X or Y?
X.
X.
It's X. So where is X 0? It's X there and there. So there's
I
actually
mixed up sine and
two
cosine.
places. And by the way, just as a, yeah, we're going to run out of time. We'll just leave it at that for now. So does it make sense? There's a billion ways to get to those two places. Don't forget, in trigonometry, in other words, if you were traveling around that circle, you're there, and then again, and then you keep going, you're there again, and you're there again, and you're there again. In other words, this up here is not just called 90 degrees, it's called 360 plus 90. It's also called 450. There's thousands of answers to each of those. That's why there's so many. So basically we could say then if t squared is equal to pi over 2, which means t is equal to the square root of pi over 2, like there would be a time. And by the way, that's the very first one. Do you understand that? That's the very first one. So that would be this one back here. Let's go check that out just to see if that's true. How am I going to do that in here? How am I going to check that out? Well, I'm going to go to that time. If I say the square root of, I can't remember how I get pi. Do we just type pi? Can't remember. Yeah, that's how I do it. I just went to that time, right? Which is apparently 1.25 seconds. Where am I? Look at that. Vertical. That's cool, right? Very first time. Well, after the start. And then where's the next time? Well, the next time would be when I got down to here, which would be when t squared is equal to 3 pi over 2. So apparently t is equal to the square root of 3 pi divided by 2. So there's the next one. But then there'd be the next one, since this thing is called pi over 2, but it's also called pi over 2 plus 2 pi. Since 2 pi is 4 pi over 2, this could also be called 5 pi over 2, right? So then the next time I would be there is when t is the square root of 5 pi over 2. That'd be the third time, right? That'd be the third time I got vertical. Let's go watch those two things, then we'll call it a day, just to see that actually happening. So that means I can just go back in here and throw a 3 in there. So I just let more time pass. Notice 3 is 2.17 seconds. It's kind of nice to see that as a decimal, like those are actually numbers. Nobody wants to say what time is it, square root of 3 pi over 2 o'clock. Give me a decimal, I know what you're talking about. Look at that, vertical, that's rad. And then we jump out to 5 pi over 2, and apparently we're vertical again. Look at that, vertical again. So interesting, it looks like the ones on the left side of that graph are the 3 pi over 2s, the 270 degree locations, and the ones on the right side of the graph are the 90 degrees or pi over 2 locations. And so they're just going to keep going. That's kind of cool, isn't it? And you might agree that I got to shut up here, I know, but you might agree that the zero slopes they look weirder, right? Like in a sense, I just got lucky. Those times are really accurate, but if I wanted to know where the zero slopes are, notice there's one right there. There's one right there somewhere. Notice they seem to be a lot more weirdly located. They don't seem to be at some clean answer. And of course, that would be when the top of this is equal to 0, right? Like when this statement is equal to 0 is when the slopes would be equal to 0. And so that might be interesting. And maybe it's the 2 in there that throws a wrench in that. Maybe it's still nice answers. But we could do the algebra for that. So that's kind of cool, right? Like we can not just, make a really kind of a neat graph that models something flying through the air in a really non-functional kind of a cool way, but we can even find interesting locations on that graph just for the fun of it. Anyway, I'm going too long. Shut up. We will actually do this a little bit more tomorrow, and then we'll jump into polar. So see after if you want to ask about your test or anything about what we did today. Otherwise, we'll see you then.
Thanks, Doug. I did have a question about the test. I sent an